David Herzog talking to us about the functional law of the iterated logarithm for weakly hypoelliptic diffusions at time zero.
Thank you for the invitation to speak here, and thank you for putting together this wonderful conference. It's nice to see people both new and older. Careful, right? Yeah. So I'll sort of admit to you that maybe a year and a half ago, I knew very little about laws of the iterated logarithm. As a probabilist, I feel like we have in some sense, a passing knowledge of these sort of classical laws of the iterated logarithm, like for Brownian motion and the standard IID sequence. But I was working on something else, and it turned out that the secret sauce to maybe get a handle on that something else, just that, laws of the iterated logarithm. So this will seem a little, maybe the topic seems a little new to a lot of folks in the room, that's okay, but it's very much relevant for, what most people will have had some familiarity with, which is the Dirichlet problem on a nice bounded domain. So here, I have a domain U, so assume everything that you want to about the domain, bounded, open, connected. The boundary is C infinity, smooth as you want. And we're trying to solve the problem LU equals 0 on the interior and then specify, some boundary data on gamma. So assume, for example, that G is, continuous in the neighborhood of the boundary. And the biggest thing that we're going to do here is we're going to assume something about the operator L. Of course, it's not going to be the Laplacian because we know a lot of stuff about the Laplacian. We're going to make the assumption that L is sort of hypoelliptic and not uniformly elliptic. Okay, so we can write L in this sort of Hermander's form, sum of squares of the vector fields, which we've all seen quite a bit by now. And so to which we can associate a diffusion, which we'll refer to as a hypoelliptic diffusion xt. So if everything was perfect, if you wanted to get a handle on the solution, you just first suppose that you have a nice solution. So a nice classical solution, right? C2 to be able to satisfy this condition in the classical sense, and moreover, continuously approach the boundary data as we get closer to the boundary, right? So if we had such a solution, what would it tell us? So what we would do, or what I would do, is I would use the method of stochastic characteristics, flow along these characteristics to kind of get a handle on what the solution should look like. And if I did that, supposing that I had such a nice solution, I'd plug it into Ito's formula, right? And this is what it would tell me, right? And of course, if this is a solution, this goes away, right? And these tau k's here, so tau k is the first time you exit sort of a sequence of domains, which increases to the full thing. So that thing goes away. And then if I take, k and t to infinity, assuming everything is nice, I arrive at sort of the nice mean value formula that I have here, where tau is the first positive exit time from the domain. But of course, there are going to be some issues with this formula. So if we look at this formula, then you can show under sort of reasonable hypotheses, so almost sure finiteness of the stopping time, for example, and hypoellipticity sort of everywhere in the neighborhood of the domain, that this formula actually defines something that solves this thing in the classical sense on the interior of the domain, right? And the issue, of course, in this context is, well, what happens as you get close to the boundary, right? And that's where problems lie. And in general, what you can prove, there's lots of examples where, this thing is just not going to satisfy the boundary condition. So as you get close to the boundary, things kind of degenerate. Okay, so the question is, so you can phrase that probabilistically as, does this stopping time, if I start from the interior of the domain, approach 0, right, as you get close to a boundary point, and 0 in some sense, so 0 in probability. This is a forward-facing talk, so there's an open problem. It's still very much open even after what I say today, but I hope that we have some sort of method to tackle this problem. So if you wanted to prove something like this, so if you believe that as you get close to the boundary, things are sort of well-behaved, how do you show that? Typically what you show is that if I start from that boundary point, that I exit the closure of the domain instantaneously. So that's what this thing says. Almost surely, it's a little weird to think about it, but that's what it says. And this is what we call a regular point. So if I start on the boundary here, it's regular if this condition is satisfied. So I exit the domain instantaneously, and we'll call it irregular otherwise. So the open problem is, this is a really hard problem, actually. So characterize all regular and irregular points for a hypoelliptic diffusion on a nice domain, for example. And so there's various works in this area in the hypoelliptic setting. Typically, they're in very concrete scenarios where they can handle this, and you can see these in these list of authors right here. There is some general kind of more analytical condition given by Alessia Kogoj more recently. But they're really like conditions, like very fine properties placed on the density of the diffusion, which are typically very challenging to actually show in practice, okay? And so the plan of the talk is to say, well, I think there's a possible way around this. And like I said before, the secret sauce is laws of the iterated logarithm. Okay, so I'll explain to you why they come into play. So we are not the first people to have this idea to use laws of the iterated logarithm. That goes back to Émile Lachal and a couple of Annals of Probability papers in the 1990s, where he was able to sort of establish these laws in a couple of examples and prove things like what we have here probabilistically. What goes wrong? So with a hypoelliptic diffusion near a boundary. So here's a half plane. This is my domain. I know it's kind of cut off, but we can modify the domain so it's smooth and kind of loops around like that if you want to make it bounded. But this here's my SDE. Let's say this is my boundary right here for a minute. We'll look and see what happens. Well, this thing is actually hypoelliptic, right? You can see like you have noise acting explicitly on the y direction that immediately goes right over here and spreads to this thing. So you're actually going to have a nice smooth density, all those nice properties that we've been seeing so far. But the issue is this sort of directed nature of this field right here, right? So if I start here, the noise is just sort of kicking me up and down in the y direction, but it pushes me in that. So you actually don't exit the domain instantaneously, right? Whereas if you compare this with a uniformly elliptic diffusion, that would mean I'd have an independent Brownian motion here on this term as well. And so you would have kind of the squiggles, right, in both directions, and therefore you would, exit instantaneously from the domain. So that's sort of the, really simplest example you can give here, okay? But it's really easy. You can obviously identify all these points here are irregular, right? But degeneracies can be a lot more complicated. So the question is, can you determine, well, I'm sorry, it's a little cut off there. I'll read the bottom, I know what it is. Can you determine if a point is regular when the degeneracy is a little bit more complicated? So we'll keep a running example, a more complicated example in mind, which would be like, we're not making the domain super complicated, keep it flat, okay, for right now. Let's take Lorentz 96 with n equals 5. There's nothing special about 5 here. It's just 5 fits on a page nicely and doesn't fit on the page as nice. But the first two directions have the Brownian motions explicitly have the random forcing. The remaining three do not. This is definitely hypoelliptic. You can check bracket conditions. It's a little bit more complicated than that last example. And the question is, so, if you look at like the upper half plane and an R5, where this is the normal direction, if I start from 0, is this actually regular for the diffusion, which is extremely hard to tell by looking at the nonlinear interactions, right? Maybe you can see it, maybe I just missed something, but it's kind of hard to tell, essentially because X5 is sort of the farthest away from the noise. And so let's talk about laws of the iterated logarithm and how they actually help here. Okay. So we go back to square zero, the 1920s. I don't know if that was when square zero was, but 1920s is a long time ago. But the first laws of the iterated logarithm. So take an IED sequence of random variables with mean, zero, and unit variance, and you look at the sum of the first n of these things. And you kind of expect to have like a square root scaling, but you can be slightly more refined than that and add this extra log n, which is the iterated logarithm, and prove something like this. So the probability that this thing happens, the lim sup is one, okay? And by symmetry, you also have that the lim inf is -1, and so you have this very precise asymptotic window on the sum of the first n random variables. And so in kind of the earliest forms of this result were proven by Kitchen and Kolmogorov in the 1920s. I think placing sort of maybe extra conditions on the moments or something like that. And then Hartman and Whitner in the 1940s here proved it for this generality. And so we're talking about diffusion. So how do we get to a diffusion? Well, we start with the simplest case, which is Brownian motion, right? ID sequence sort of naturally maps onto Brownian motion, right? And nothing changes. Okay, the result is exactly the same. The scaling is exactly the same. And so you have, again, this very tight window, lim sup, lim inf, plus or minus 1 on the Brownian motion, but this happens at time infinity, right? But we want to understand what happens at time 0, okay? And so to get something at time 0, you have to for Brownian motion, use time inversion, right? Okay, so to get back to time zero, right, you just use the scaling t w1 over t, and as long as you define it this way, this gives you a Brownian motion. And then so when you translate this result back to time zero, you arrive at a law of the iterated logarithm for Brownian motion at time zero. So the only thing here that changes is that t becomes t to the minus 1. But you can say even more about this, okay? We can be even more refined about this LIL. We can deduce one in a functional form. So now if you say, well, I understand that this is kind of the right scaling for the Brownian path or the Brownian motion. What happens to the path, okay? So if you rescale Brownian motion like this way, think about this as a continuous path on the interval from 0 to 1, you may wonder if this process yt does something meaningful as epsilon goes down to 0, okay? In particular, can you characterize the set of limit points, okay? And indeed you can. So the set of limit points in the space of continuous path, I think about this as kind of a control set, okay? So the set of limit points in the space of continuous paths for this thing is the set of all continuous functions which vanish at 0, whose time derivatives are in L2 with this norm bounded above by 1. So the way that I think about it is, okay, whatever kind of control path that I can make from this, whatever that belongs in this set, essentially I take a small window about it. This path belongs in that window infinitely often as I go down to time 0. So the earlier form of this functional form was due to Strassen for an IID sequence. And you can see kind of the work of Mueller for Brownian motion at time infinity, Nina Gannert at time 0 for Brownian motion, and then these really seminal works of Baldi and Caramelino in 86 and 89 often go, I think he's time infinity and time 0. So there's always this relation going back from time infinity to time 0 in this business. Okay, so let's think for a minute about what is it. So why would this be important? Okay, so before I go on to the next slide, let's just think flat domain, upper half plane, and I have Brownian motion, right? Started here. What happens, right? I go back and forth here infinitely often, almost surely, which proves that I'm regular at this point, right? And so that's the connection to LIL, why you would want to do this. So why you want to figure out the LIL for these things in a hypoelliptic diffusion, because that's what you should be using to show this property. Oh, but how do you get from something that's elliptic to hypoelliptic? Okay, it's kind of an analytical method. We'll use scaling, right? So let's take again a simple example. This is like your simplest hypoelliptic diffusion. This is the Kolmogorov SDE example of a hypoelliptic diffusion that's not uniformly elliptic, provided to us by Kolmogorov. And if you start from 0, so basically I'm just going to take Brownian motion and integrate it once in time. Okay, this is hypoelliptic, very, very easy to see. And of course, I just do the same scaling for the first direction. So I rescale this. And if I was thinking about, okay, what if I kind of rescale the second direction? Can I arrive at some kind of maybe control problem that would tell me what trajectories are going to be in the limit set? Okay, and that's the basic idea. It's very simple. I keep x2 on the same time scale, and I have to figure out what the height function needs to be so that I get something meaningful when I take epsilon down to 0. Now, what should you be choosing this to be? You should be choosing this so that epsilon over h epsilon gives you whatever you need for this to be y1, right? And that choice is, of course, right, root 2 epsilon cubed log epsilon inverse. Of course, right? It's whatever. It's that epsilon over h epsilon equal that. That's what it gives you. Just a little algebra, but that's the right choice. And okay, so what does it tell us? So you got this rescaling, you got this kind of path rescaling, and how do we get to the end result? So you write down the SDE for this y process. Of course, that's what we saw how we constructed y2 so that it satisfied this equation. But what did I do here that's a little differently is that I'm on this new epsilon time scale. I sneak the root epsilon that I had here before into the Brownian motion. So in turn, I get a new Brownian motion. And what's happened, right, is that this term is actually blowing up, right? And so enter large deviations theory, right? Okay. So there's a big gap in between what I'll put here and next is that indeed you do have the same result, okay? But you have to plug it into large deviations theory. redo quite a bit of it, in fact, to make this work. I'm sorry. Oh, we got most of it on there. It's fine. This is a really simple example. We can do a lot more examples. There's a general result, but this is the kind of thing that you can prove. So for almost all omega, the set of limit points of this process coincides with a collection of these trajectories, where this f, of course, is sort of belongs to this control class that we saw before. Okay, that's cool. So let's go back to the original question again in this context. So in the y2 direction, do we have those oscillations? Indeed, we do. Okay, so you solve this control problem. Of course, you can steer this path y2 to both positive and negative values at time 1. Okay, and if you evaluate this result basically at time 1, right, then you have something like this, that the lim sup of this thing is some positive number m, and the lim inf is minus m by symmetry. And again, these oscillations back and forth across this really nice flat domain. Okay, so this functional form is much stronger, right? Because you have a ton of information. Yeah, I mean, you don't need all of that information, but I think to get at this problem, you really need that. Okay, so this is a really nice simple example. How am I doing? I'm doing okay on time. What about Lorentz? Okay. So I won't actually go through each scale, okay, how you get at each scale here. But again, you would do the same rescaling for Brownian motion that we had on the first two things. None of this stuff here matters, right? Because this is clearly the dominant part of the equation at time 0. And then now if you kind of understand that the next sort of largest direction here, started from time 0, will be contained in these two terms, then these two terms, and then those two terms, you would arrive at this. Okay, kind of interesting, weird things like just powers of epsilons, right? And powers of log epsilon inverses. Just kind of interesting. So when I think about these things, I automatically think of Hermander's smoothing estimate somehow, right? So there's these powers here that kind of correspond somehow, but I can't make anything of it other than it seems to be loosely related, right? Okay, but that's how you define the remaining directions here. And the answer is very much the same, okay? So we define y1 and y2 according to the Brownian scaling, but again, you get a slightly more complicated control problem to solve, right? But you can do it. You can actually solve it and indeed prove the thing, that I was saying in the flat domain, that in fact, that is regular for that. It takes somebody like Uri Folds to see how to choose them just appropriately, so you get positive and negative values in the control problem. It's not symmetric in this case.
But can't you? It looks like it's odd, right? Relatively odd.
It is. It's relatively odd, but it's a little different. Like these things are not though. It's not as easy as, because if you solve this like directly, because this is just completely integrable, you just integrate all of these things.
Right.
You can't just go +1, -1 and get what you want at this last direction. So it's different than that. We had to choose some oscillatory functions to actually see that you could achieve both positive and negative values.
I see. So you're telling me you can't bang control it.
No, can't bang control it like we're used to. So these are a little bit new, and I'm not sure exactly how to deal with them yet. So, okay, so notice here again, I got rid of 2's here, but I paid a cost of a 2 here, but it doesn't matter. There's always a lingering 2 in stochastic analysis, and that's where it is today. Okay. But that's the vision. Okay, so you have to figure out the law of the iterated logarithm. I've only done a couple of examples, and these are fairly simple examples. So you make them more complicated. You start from a generic initial condition on a non-flat boundary. Everything is much more complicated, of course, but this seems to be the right thing to do, right? And so the open problem is, how do you make this work in more generality? Our vision, this is not our vision. Everyone would have the same vision. So can't claim this is like the vision in Evan's book when you talk about just standard method of characteristics. So when you want to solve this, right, you don't start with the curve thing. You flatten the boundary locally, right? So that's why I was doing all these flat boundaries, right? So I first say, okay, here, flatten the boundary locally, I get something else, right? And I shift to 0. So I start from 0. And now the idea is, okay, you have to determine whether or not you get a law of the iterated logarithm that tells you that you do these oscillations. And so basically, what we can do is sort of, you give me a concrete example, I can probably sit back and figure out how to solve the control problem, find that determines this functional LAL, and maybe analyze the regularity problem by solving this and mapping back to the original dynamics. But that's all I can do, and that's all we can do. And so, really, I don't know what to do here, but I don't know how to find a structured way. It's just different. Like, how do you find a structured way to compute the scalings, right? That would be a really good start to figure out, what you do. They very much correspond to brackets, right? You notice that like those are all the brackets that you see in here, but it's different because you need to keep track of directionality in the problem. So somehow it's a little different. So if you started out by just saying, I could find a structured way to do this for polynomial ODE perturbed by some additive noise started from the origin, that would be great. But if you wanted to do this in more generality, say you want to have state-dependent noise, I didn't talk to you about the obstacles in the large deviation theory. There's significant obstacles in the large deviations theory to make the results work for state-dependent noise. And it's essentially at the level of, we know that additive noise, things kind of continuously depend on the noise, but for non-additive noise, they do not. And you need those continuity properties in the large deviations theory to make these things work. So do you need to do something with rough path theory? Okay, I don't know, because I'm a little less familiar with rough path theory, but okay, I'm done. That's all I have to say. Thank you.
Any questions for David?
Sure.
So your analysis also suggests the optimal regularity at the boundary. C1/2 or something.
Yeah, maybe. Yeah. So I don't know. So I don't know how to actually get this back to sort of like a smoothing estimate, but maybe there is a way to do that.
I mean, I assume that your definition of regular points aligns with the normal definition of regular point.
Yes.
Boundary data is obtained continuously.
Exactly.
So I just, asking.
I don't know. So I don't know if you, maybe you can prove something like you have some sort of regularity estimates locally. I think probably something like they're probably density estimates or something like that, where you have the precise scaling in time and whatnot. I don't know how to do that. I don't know how to get from here to there, if that makes sense. Doesn't matter.
Thanks. So I feel like maybe had just zoned out for a moment, but when you were discussing the kind of general program, you can solve it in a specific case, solve the control problem. Are you saying that if we want to solve it more generally, we should try to do something other than control problems, or should we come up with a gadget to like automatically solve control problems?
Exactly. The second thing you said.
The second one.
Come up with a gadget. It seems possible, but I don't know how to do it.
Yeah. Given how much I know about control theory, I have no idea.
I mean, the control problems aren't particularly hard. They're definitely integrable. Like you can solve them, right? But you have to determine signature in one direction, which is a little challenging, and especially in that Lorentz direction, which like Jonathan said, well, you should be able to just say like it's positive and negative sign just by like plugging in plus or minus 1 for the control, but you can't do that in that example, which is a little strange. So we had to use oscillating functions like cosines.
So you need to like worry about the shape of it.
Yeah, absolutely.
Thank you very much. Maybe two things.
Sure.
I could think about it. Maybe one of them is take a Caroteodori distance instead of the Euclidean distance.
Okay.
And see what is the relation between your rates, to see whether that's order has something to do with that distance. I mean, you already talk about related to the number of brackets needed, but the distance maybe, if I look at the distance with the scaling, maybe that's uniform way to see it.
Yeah, that makes a lot of sense actually. Yeah, I mean the control distance, right? Yes. Yeah.
And kind of relatedly, you can also separate maybe into like thinking about the quadratic variation. There's like you think of it as a map in the path and the quadratic variation of the path, right? Which is a little bit about path, but it's not related to the character. Some of those things you might get different scale. That's why you might get this weird, not just increasing. Depend on those two parts, right?
Yeah.
Because the law of logarithm is a quadratic variation object somehow.
The second way to do it, I think, is maybe to smooth out your y, so it's not too singly blow up a bit, then take it to closely to y square afterwards, and to see how the singularity when you converge. Well, I'm thinking you take a function phi epsilon of y, converge to y square. But it's not really it doesn't have a zero, you smooth it out, you smear it, average it out on the small ball,
I see.
and then take it.
So do some averaging first. Yeah, so this is like I said, this is a fairly new-ish thing for me. I mean, like I said in passing, but it's sort of interesting, right? It's like the right thing to think about. But yeah, it's new in the sense that, have another question, Jonathan?
Well, I was also wondering, I mean, there's some work, like things like maximums, right?
Yeah,
And things like that are known to be, even though they look not smooth at first, they're actually smooth from the point of view of kind of the Wiener process, right?
right.
And there's some work, I remember, I thought like maybe Vlad did some work, or maybe Yuri did some work on kind of Malevin differentiability of exit times.
Uh-huh.
I was wondering if you thought about that kind of stuff.
No, I mean, I've heard of some of that. Is it Malevin differentiable, the stopping time with respect?
I'm not sure. I was just thinking, I mean, I know
Yeah.
they did, I know Yuri did something. I can't remember because he asked me some questions at the time he was doing it.
Uh-huh.
Are you checking to see if he's online? No,
Yeah, I
he's-
didn't know if someone popped up
No.
a question. I saw something too.
Yeah. So I was just wondering if you explored that and turned away from it.
No, I didn't explore that actually. No, but I've heard about that, but
Yeah.
I've never.
Yeah.
I've heard I think someone once told me that stopping times are like 1/2 Malevin differentiable or something different like that. Malevin once said that. Like I think so I had a conversation with somebody about this. I don't know if this is actually true, but no, I haven't thought about that. But maybe that's another way to think about it.
Because you can look anyway.
Let's think.